Welcome to my course, Testing Automation, the Big Picture. In this first module, we're going to get an overview of what testing automation is and also the business value that it may bring. So in this first module, we're going to start off by looking at exactly what automated testing is. We'll then move on to discuss what the high-level benefits are of automated testing, before discussing the total cost of ownership of software. In addition to the potential monetary benefits, we'll also discuss the happiness factor that automated tests can help us deliver, and we'll discuss automated testing in the wider business context. While automated tests can bring considerable value to the business, we'll also discuss some of the considerations to bear in mind when using automated tests. And finally, we'll discuss the difference between short-term and long-term delivery speeds, and how automated tests can help us here. So let's kick off this module with a discussion of what automated testing is. So if we're not currently using automated testing, we may be testing the system by using human testers. In this scenario, a human tester will generally be working from some sort of test script. So this test script could be inside a Word document or perhaps inside some third-party manual testing system. Our human tester here will open various test scripts and then execute the system, interacting with it as specified in the test script. Once these interactions are complete, the human tester here will obtain some results and compare those to the expected results outlined in the test script. Our tester here can now report the outcomes to the rest of the project team. If the obtained results don't match up to what was expected in the test script, then we can say that the test has failed, but if the results that were obtained match those that were expected as outlined in the test script, then the test has passed. The two biggest changes for automated testing is that the human tester here is now replaced with a computer. So it's the computer's job to interact with the system that we're testing and obtain the results. Because the computer has to execute the test now, we can no longer use a Word document, for example. Instead, we use test code. This test code specifies how to create an instance of the system that we want to test, which interactions to perform against the system, and then the expected outcomes. Just as with our manual human testing, our automated tests can fail or they can pass, and the developer or the team can take appropriate actions based on the outcome of the automated tests. Let's take a look now at some of the high-level benefits automated tests can give us, and we'll also compare them against manual human tests. First off, automated tests are essentially free to run as often as required. Other than any costs for electricity or hardware, for example, we can run them over and over again, and they're essentially free. Human tests, on the other hand, cost us every time we want to execute a test run, and this cost is primarily a staffing cost. We can run automated tests at any time of the day or night. They can be executed after each piece of work a developer finishes, or scheduled, for example, to run at midnight. Manual human tests, on the other hand, are limited as to when we can run them, depending on if we have staff in the office. Automated tests can execute more quickly than the equivalent manual human tests. Automated tests are generally less error-prone. Assuming that they've been written correctly, and all other things being equal, they should produce the same pass or fail results in a reliable way. Manual human tests are potentially more error-prone, and this is just simply due to the human factor here. For example, we may get tests passing that should have failed, or incorrect defects being raised. Automated test code can sit alongside the production code that it's designed to test, so for example in some source control system. This means that if we're working on multiple releases, for example, we can create branches in the source control system, and this means that the test code will always be in sync with the production code that it's designed to test. Manual human test scripts, on the other hand, may exist in some kind of external system, for example a Word document in SharePoint. This means that it's possible for the versions of the test scripts to get out of sync with the actual production code that it's designed to test. Once again, this may mean that defects are missed, or defects are raised by the manual testers that aren't actually defects. It's worth bearing in mind here, though, that automated tests do have a creation and maintenance cost, and so do manual human tests. While we're on the subject of costs, let's take a look at the cost of defects as found in different phases of the software development process. This is a great quote that sums this up by Curry and Brisky and others. Minimizing defects is one of the most effective ways to keep development costs down. In a report by the National Institute of Standards and Technology, we get some idea of the relative cost to repair defects when found at different stages of the software development process. So along the bottom of this chart we have the different software phases, including at the end the post-product release. So in these examples, the relative cost to repair a defect when found in the requirements gathering, analysis or architectural design phase is 1 times. Once we move to the coding or unit test phase, the relative cost to fix a defect increases from 1 times to 5 times. So it's 5 times more expensive to fix a defect here than it would have been in the requirements gathering phase. Once we move to the integration and component system testing phase, the relative cost increases to 10 times. And in the early customer feedback or beta test phase, the relative cost increases to 15 times. But look what happens when we find a defect in production. The relative cost increases to 30 times. So we've gone from 5 times the relative cost at the coding or unit test phase, right up to 30 times the cost to fix it once it's released to production. Let's take these relative costs and plug in some actual monetary values. So here the cost to fix a defect at requirements gathering stage is $100, so this is our 1 times multiplier. At the coding or unit test phase, we increase this by 5 times to a cost to fix of $500. The integration and component test phase, the cost increases to 10 times or $1,000, and at the beta test phase, 15 times or $1,500. And post-product release, this is our 30 times cost, in this example, $3,000. So for example, if we use these sample costs and plug them into a scenario here. In this first scenario, we're simulating a poor testing strategy in the organization. This scenario is characterized by defects being found later on in the development process. So in this table, we can find that we've got 1 defect found at requirements gathering, 5 in the coding unit test phase, 3 in the integration and component test phase, 10 in the beta phase, and a whopping 30 defects found post-product release. We've got a total of 49 defects found, and this equates to a total cost to fix all of these defects of $110,600. If we compare this to another scenario here, in this scenario we're simulating a better testing strategy, and this is characterized by defects being found earlier in the software development lifecycle. So here we can see in scenario 2, we've only got 10 defects found post-product release, and we've got a large increase in the number of defects found at the coding or unit test phase. We've still got a total of 49 defects found and fixed, but this time the total cost to fix these defects is only $60,600. So this means in scenario 2, we've got a defect detection cost saving of $50,000. So why does it cost so much more to fix a defect once it's made it into production than it does at coding or unit test time? Well, let's go through some of the steps here. If we find a defect at the coding or unit test time, typically this could surface by a unit test failing in development. The developer can review the specific failure message for that test, go ahead and fix the code in development, and now the test passes. However, if a defect is found in production, there can typically be a lot more involved to fix it. So here we have the error occurring in production, and this could be identified by some kind of automated monitoring or reported by an end user. The production bug is logged or a ticket created in some kind of bug tracking system. Next, the developer has to get access to the production logs, and once they've got access, they need to trace through the logs to try and determine the cause of the error. Once the probable defect has been located in the logs, the developer can try and reproduce it in the development environment. Once the defect has been reproduced in development, the developer can go ahead and implement a fix. Once this fix is tested in development, a new production release can be planned that will implement the bug fix. We can then release the bug fix to production, and hopefully this won't mean an outage for the end users. And finally, we can check that the bug fix actually works in the production environment. So I hope this comparison serves to illustrate how fixing bugs in production can be a lot more costly and time-consuming than to find them at coding or unit test time. Now we've got an idea of the potential cost savings of automated tests, let's also consider how automated tests can help increase the happiness factor. So automated tests can result in happier end users of the software we're developing. They can accomplish more tasks and feel more productive in the time they have because they encounter fewer problems with the software getting in the way. Automated tests can also help to create a happier development team. This means the team can spend less time fixing production defects and instead focus more time on developing new and potentially exciting features. Because we have automated tests in place to find any errors, we can have increased confidence to make changes in the system. Automated tests can help to document the system we're building and increase the overall system understanding that developers have. And finally, we can have a happier development team if we have less unnecessary stress caused by a constant barrage of production errors. Automated tests can create happier business owners. This can happen from reduced costs of finding errors in production or increased revenues from less system outage time. Higher quality software may improve the business reputation. Customers that use a company's software that's always experiencing problems may form a negative view of that company and also pass on that negative view to family and friends. Because we've got a happier development team, this may reduce development team staff turnover. The development team is happy enough that they don't see a need to move on to another company. This creates long-term consistency of both development practices and also support knowledge. This also reduces the cost to the business of finding and recruiting replacement team members. Automated testing is not the be-all and end-all of the quality story when it comes to software development. Let's take a look at some of the other things that can affect software quality. So we've got additional techniques that we can employ in addition to automated tests. Techniques such as formal or informal code reviews. This is where one developer reviews another developer's code to check for any obvious errors. There's also the related technique of pair programming. This is where two developers sit down at the same machine and code together. Other factors that can influence overall quality include good management and management practices at the organization, a happy and motivated development team, well understood requirements. Even if a feature makes it to production with no obvious errors, if that feature doesn't fulfill the end requirements of the end user, then we have a problem with the quality or the understanding of the requirements. Finally, software development doesn't sit on its own. We need somewhere to deploy this software to. So good environment configuration and management, and also a healthy DevOps culture can contribute to the overall quality of the system. While automated tests bring a number of benefits, there's a number of things to consider when implementing them. First off, if the developers aren't as experienced with automated testing, then there may be some training or upskilling costs for the development team. You may need to purchase new hardware. This might involve upgrading the developer workstations to be able to execute the automated tests in a timely fashion, and it may include buying new servers on which to execute tests. If we do need to purchase new servers, then there may be operating system license costs associated with this. And if we're using any third-party commercial, non-open source testing tools, there may be additional license costs here. When we start to implement automated tests, we may get an initial downturn in productivity. And this is because creating automated tests requires some investment in the form of developer time. We also need to consider what the time to market is for the software we're trying to deliver. Let's delve into these last two items in a little more detail. So there can be some trade-offs when considering automated testing. For example, the short-term versus the long-term delivery speed. So here we have a chart, and along the bottom here we've got different releases of our software application. Let's consider two approaches here. One is to maximize the short-term speed. So for example, if getting a product to market is the most important thing and the level of quality is not as important, then we may optimize for the short-term speed. We may instead consider that the long-term delivery speed of the project is more important than the time to market for the first release. So both of these approaches start at the same point on the graph, the project start, but notice here that if we optimize for short-term speed, the time to the first release might only be 1 month of development work. This is because we're not investing heavily or at all in automated testing. The version here where we're optimizing for long-term speed takes us a little longer to get to the first release. In this simulated example, the first release doesn't come until 3 months into the project. We can continue to optimize for short-term speed, in which case we can get the second release deployed to production in only 3 months, whereas the long-term speed approach has taken us 4 months to get to the same place. However, at some point during the software's lifetime, optimizing for this short-term speed is going to start to slow us down. At some point these two lines will cross over, and as we add more features to the application, it becomes harder to manage. We may end up with more defects, which require more time to fix. So here, to get the third release to production, the short-term speed has taken us 6 months now, whereas the long-term speed approach is starting to pay off here. It's only taken us 5 months to get this to production. To continue this example further, release 4 in the short-term optimization approach has now taken us 12 months to get to release 4, whereas because we've optimized for long-term speed with good tests and testing infrastructure, we can continue at a steady pace. In this case, rather than 12 months, it's only taken us 6 months to get to release 4. And we can continue this onwards. When starting a project and considering the testing approach, this short-term versus long-term delivery speed trade-off should be taken into account. If the most important thing is to get something out of the door, for example to capitalize on some niche opportunity before another company does, then missing out on this potential opportunity may be more costly than the reduction in long-term delivery speed. However, if more predictable delivery times are required, or the software system is considered critical in some way, so for example internet banking, or perhaps some medical application where lives depend on it, then our testing strategy may align more with the long-term speed approach. So that brings us to the end of this first module. In this module we started off by getting an understanding of what automated testing is and how it differs from manual human testing. We learned about some of the high-level benefits that automated testing can bring, such as the fact that they're quick to execute, and essentially free to execute as many times as we like. We considered the cost of ownership of software development, and that if we find errors in production, this may cost more to fix than if we had found them in development. We learned that automated tests can help us to deliver happier end users, a happier development team, and a happier business. We also looked at automated testing in the wider context. So for example, how it's just one aspect of software quality that can be augmented with code reviews and well understood requirements. We learned about some of the considerations that we might want to bear in mind when using automated tests, such as any training, hardware or license costs, and also how much of a business driver time to market is. For example, are we going to optimize for short-term delivery speed or try and optimize for a more predictable long-term delivery speed? Join me in the next module when we'll begin to get an understanding of the different types of automated tests we can create and how these different types of tests fit together in an overall testing portfolio.